This is chapter 9 of the Watson text. This chapter is about solving games using the Nash equilibrium concept. A Nash equilibrium is a stable point in which all players in the game are playing a best response. In a two-player game, a Nash equilibrium can be thought of as a point of mutual best response. Equilibria are simply stable points. As such, a point of unanimous best response is stable. If everyone's in best response, or if everyone is best responding to the set of other players' strategies, then there do not exist incentives for unilateral deviation or deviation by one player. Best responses, we might say, are mutually reinforcing. Indeed, a unilateral deviation would constitute a change from a best response strategy to a strategy that is not a best response. And so that's not really a justifiable type of deviation. On the grounds of rationality, we can't really justify someone moving from a best response strategy to a strategy that is not a best response. So in this sense, we call best response strategies mutually reinforcing. If we're all at a best response, then each best response reinforces the other to create stability. Formally, a strategy profile S star is a Nash equilibrium if and only if, well, each player's strategy in that profile is a best response to each other player's strategy. So this first line of the definition just says each player's strategy within that profile, that Nash equilibrium profile S sub I star, is in the set of best responses to the other player's chosen strategies in the profile. And this is true for each player I. So in other words, it's just saying that every player is playing a best response to the other player's strategies. Another way of saying this is that the payoff to player I in the strategy profile S star is greater than or equal to the payoff to player I from playing any other strategy, given that all of the other players stay within the profile S star. And this is true for all alternative strategies Si prime in cap Si. So, and what this second line of the definition says really is that if it really is a Nash equilibrium strategy, then you can't do any better by playing an alternative strategy, by unilaterally deviating from that strategy. So how do we calculate Nash equilibria? Well, for two-player normal form or matrix style games, we calculate best responses to individual pure strategies by drawing our best response arrows, and then we find cells with all arrows toward, or cells in which each player is best responding to the set of other players. And so we call these strategy profiles Nash equilibria in pure strategies. In general, there can be 0, 1, or more than one equilibria in pure strategies. By impure strategies, it is meant that the equilibrium does not involve mixing between strategies for any player. Within the equilibrium, each player does the one thing. They employ one strategy with certainty. Some equilibria, we call these mixed strategy Nash equilibria, involve mixing between pure strategies. For example, in pitching, you're never going to have, unless it's a very overpowering pitcher, you're never going to have a pure strategy Nash equilibrium that involves the pitcher just pitching a fastball every time. Typically, pitchers will mix between fastball and, for example, breaking ball. And you'll never have a batter on the other side of the game who always times for a fastball. The batter might time for a fastball or a breaking ball depending on the mixed strategy equilibrium that's employed. John Nash showed that for games with finite set of strategies, an equilibrium exists in pure or mixed strategies. So what this means is if we get zero Nash equilibria in pure strategies, by doing our best response analysis, we should look for a best response or a Nash equilibrium in mixed strategies, and I'll show you how to do that in a future chapter. So if you get no pure strategy Nash equilibria, you should look for a mixed strategy Nash equilibrium. Let us consider a Nash equilibrium solution example. So in this game, consider a river that borders two countries. These countries independently and simultaneously choose whether to use the river intensively or sustainably. Simultaneous choice is not always a literal assumption. Players may not choose at the same exact moment. However, this assumption simply means that I don't benefit from knowing what you will do when I make my choice, and you don't benefit from knowing what I will do when you make your choice. In this game, if used intensively enough, the river will be depleted and polluted and will have limited downstream or next period use. So this is another tragedy of the commons style game. Okay, so this unregulated river usage game appears as follows. On the left-hand side, we can show it using this game matrix. There are two countries. Country 1 is the vertical or row player. Country 1 can choose low river usage or high river usage. And because this is a border river, there's a second country, and so country 2 has the same choice between low and high river usage. High river usage might be taken as high polluting, or you're drawing from the water unsustainably, you're drawing from the river. But however you take it, high use is unsustainable if you want to keep this river the way it is and use it as a valuable resource in subsequent periods. Okay, so we have our players, we have our strategies, we have our payoffs, and that first payoff in each cell applies to country 1, the second payoff applies to country 2. And I also have some bracketed numbers, meaning I'm attaching that each of these arrows in the best response analysis to an explanation on the right-hand side of this slide. So that first arrow says, if we look on the right-hand side, that first arrow, which is an arrow down in column 1, okay, it says, if country 1 believes that country 2 will choose L, thus putting the game in the first column, then country 1's best response is H. And the reason for that is country 1 will get 7 units of payoff if they choose H in this case, and they'll only get 6 units of payoff if they also choose L. Okay, so if country 2 chooses L, or if there's a belief that country 2 will choose L, then the best response for country 1 as a payoff maximizer is to choose H. Okay, so that's best response arrow 1. Best response arrow 2 also applies to country 1. It's a vertical response. Okay, and what it says is that if country 1 believes country 2 will choose H, then country 1's best response is to also choose H, because 4 is greater than 2. Under this condition, country 1 believes country 2 will put the game in the second column. So therefore, under this belief, country 1 can get 4 units of payoff from choosing H, or only 2 from choosing L. So as a payoff maximizer, as a best responder only, we're not talking about ethics in this case, we're just talking about payoff maximization. As a payoff maximizer, in this case, country 1 would choose H over L. Okay, the next two best response arrows apply to country 2 for given beliefs of country 1. So arrow 3 is that topmost horizontal arrow, and it's an arrow right. It says that if country 2 believes country 1 will choose L, then country 2's best response is to choose H, because 7 is greater than 6. Okay, so we're thinking about country 2. and we're thinking about second payoffs, that is country two's payoffs, for given beliefs about which row country one will put the game in. So if country two believes country one will choose L, thus putting the game in the first row, then country two is better off choosing H and getting 7 than choosing L and getting 6. And lastly, best response arrow 4 says that if country 2 believes country 1 will choose H, thus putting the game in the second row, then country 2's best response is H, because they'll get 4 if they choose H under this belief, and 2 if they choose L. So as you can probably see then, the Nash equilibrium is HH. Each country uses the river intensively, and so they get a payoff of 4 units per country, and this is an inefficient outcome. They could each get 6 if they used the river more sustainably. And we often see this in border rivers or border lakes that are unregulated, that it's a tragedy of the commons or inefficient outcome. A best response is to use such resources intensively, because really you're afraid that the other party will. So whether or not you want to use them intensively, you're afraid you will exercise restraint. The other party will use the resource intensively and you'll lose out. Let us now consider a variation on the river usage game in which river usage is now regulated. Namely, let us assume that the countries joined a regional environmental pact. The pact will fine any high-intensity river user by 3 payoff units. Now the river usage game appears as follows. So this is like the unregulated river usage game in several ways. There are 2 countries. There's still a border river. Each country can choose low-intensity use or high-intensity use. The only difference is every time a country chooses high-intensity use, they will be caught, is at least the assumption of the game, and fined 3 payoff units. So any payoff that is supported by high intensity river usage, we subtract a 3. Okay, so for example, when both countries choose high, instead of 4 being the payoff, now we have 4 minus 3 and 4 minus 3, or 1. Okay, if they both choose low, they're still at 6, no one's fined. But if country 1 chooses low, country 2 chooses high, so we're in the top right corner, then, well, country 1 still gets 2 units of payoff, but instead of getting 7, now country 2 gets only 4 units of payoff. Okay, and the same logic explains why in the bottom left corner we have payoffs of 4-2 instead of 7-2. These fines are enough to change behavior and to change actually the dominant strategy of the game is now low intensity river usage. Okay, such that the Nash equilibrium, the cell in which all arrows point toward, is now low intensity use, low intensity use. That's the Nash equilibrium. And the Nash equilibrium outcome is 6-6, and this is an efficient outcome. Okay, so merely by imposing a regulation that's not even used because it actually changes behavior in a desirable way, we have effected an efficient outcome. But let's explain these arrows. Again, there are 4 arrows. The first arrow says that if country 1 believes country 2 will choose L, thus putting the game in the first row, then country 1's best response is L because 6, a payoff of 6 is greater than a payoff of 4. Okay, let's talk about the second arrow, which is also vertical. Also pertains to country 1's best response to beliefs about what country 2 may do. So arrow 2 says that if country 1 believes country 2 will choose H, then country 2's best response is L because a payoff of 2 is greater than a payoff of 1. Okay, arrow 3, which is the topmost horizontal arrow, and it's an arrow left, says that if country 2 believes country 1 will choose L, thus putting the game into the first row, then country 2's best response is L because 6 is greater than 4. And the fourth arrow or the bottommost horizontal arrow says that if country 2 believes country 1 will choose H, thus putting the game into the bottom row, then country 2's best response is L because 2 is greater than 1. The regulation in this case changes the outcome from one of inefficiency to one of efficiency. This regulation is effective in changing behavior in a desirable manner, even though no fines are actually levied in the new equilibrium. And really, this is the hallmark of an effective regulation. This regulation is not designed to collect revenues. It's designed to create economic value by changing behaviors in a socially desirable manner. The regulation creates 4 new units of payoff by changing payoffs from 4-4 to 6-6. Each country now gets 2 more units of payoff.